Uh, Good morning, everyone. My name is Shikhin Seti. The topic of my talk is Option Rooms, a hidden but privileged world. The hidden in my topic title is a bit of a misnomer because option rooms really are not hidden. Each one x86 computer has option rooms in them for various little things. So the agenda of the talk would be a slight introduction to option rooms, what option rooms really are, the motivation for this whole talk, prior work on exploits using option rooms. Then I look at various exploit mechanisms for both BIOS and UEFI. And then I look at further work in the area and preventive mechanisms for such exploits using option rooms. So firstly, what's PCI? PCI is a specification which describes a bus to attach either peripherals or other buses to the main bus. So in your computer, you have a host to PCI bridge, which attaches the host bus and the root PCI bus. Then the root PCI bus is connected to either the ISA bus, the interrupt controller, the USB IDA DMA controllers. Then you can have further PCI to PCI bridges for recursive structures in the whole connection. So why do we need option rooms? Each device in your computer requires code to initialize themselves, to carry out self-test using the post. Then they require code to interface with the firmware because the firmware might need the device. So on BIOS systems, these are divided into devices which are output devices. For example, MDA, CGA, EGA, VGA. All of these have option rooms for initialization. And then the BIOS needs to find the boot device. For that, you need to enumerate all devices capable of boot, initialize them, and then perform I/O with them. So output devices require interface for changing display modes. You might have text modes and graphic modes. And then you would either require to output text or output pixels, raw pixels. And then boot devices are divided into two categories. One are directly read-writable storage, for example, SCSI controllers. And then you have directly bootable protocols, like the PXE, for which you don't have the write part. And there's a slight difference, which I'll cover later. So option rooms are initialized by the firmware using the PCI configuration space. The configuration space table is shown on the right. And the firmware writes in the expansion room base address register, which specifies the base address in physical memory for the option room. It must be aligned to a 2 kilobyte boundary. And the lowest bit in the register is called the memory space bit register, memory space bit, and it enables the expansion room. Now, option ROMs are stored on either EPROM or EEPROM. For rewriting EPROM, you need ultraviolet light, but for EEPROM, which is more common on most devices, these can be erased electronically, and thus they can be reflashed by the operating system. Now, option ROMs lie in either the C0000 to C7FFF boundary, or till F0000. The first part contains on VGA ROMs, and the second part contains non-VGA ROMs. The VGA ROMs is for the output device, and non-VGA ROMs might be your network card, or your hard disk controller, or anything. Each option ROM has a small option ROM header. The option ROM header starts with the same signature used by boot sectors, followed by the length, followed by the initialized entry point, and then for the data. The firmware first enumerates all option ROMs, maps them to memory. Then the firmware jumps into the initialization entry point for each option ROM. The ROMs then initialize, The ROMs then initialize their devices and hook onto each interrupt as required. Then each option ROM, following with the BIOS boot specification, has a PNP expansion header. The PNP expansion header basically specifies how the option ROM can boot, if at all, and some other data. Now, with the PNP expansion header introduced, the option ROM in its initialization code should not override any interrupts. All it does during initialization is initialize the device and then return a boot capabilities flag. The boot capabilities flag, as shown in the table below, lists down whether it is an input device or not an input device, whether it is a display device or not a display device, and whether it can boot or not. If it can boot, you have to specify using the highest bit whether it is a block device format. And if it is a block device format, later on it will hook the N13, which is used for reading from the output device, storage device. Now, with the PNP expansion header, devices can either be boot connection vectors or bootstrap anti-vectors. Boot connection vectors hook the respective interrupts, and then the BIOS continues with the boot and uses the interrupts for reading from the storage device. With the bootstrap entry vector, you have to directly boot the system. It is used for example, network-capable devices, and it should not return the N13H block device format, for it doesn't support that. So PXE uses this. Now the motivation for the talk. All bootloaders, all of them use services provided by option ROMs. And so a device can have malicious ROMs flashed by someone else. And furthermore, several OSs like Windows switch back to real mode to rely on services provided by these option ROMs. So the security of these option ROMs is a real concern. Now UEFI provides opportunity to do away with the legacy mess. We can introduce a generic format for all these option ROMs. Earlier on, if your device wants to support multiple platforms, you have to chain the option ROMs. You can have an option ROM for x86, then you can have one for PPC or something else. With UEFI, they have introduced a bytecode format, so you can do away with all duplication for the code. Now, prior work in the area. The most important paper in this area was by John Heisman in Black Hat DC 2007 called Implementing and Detecting a PCI Rootkit. He started with how to reflash option ROM. This is only possible with EEPROMs, of course, and for that you require I/O with the card. Now, what happens is that your kernel code runs in ring 0 in x86, and normal user space processes run in ring 3. And you've got a IOPL, or I/O privilege level, which specifies which ring level can do I/O. I'm so sorry. And on Windows, normal processes operate with the IOPL of 0. What John Heisman said was that you can elevate the IOPL using the native undocumented function NT-set information process, and then elevate the IOPL of a normal process, and then a browser exploit or anything can do I/O with the card and flash it with a malicious option ROM. Now he further went on to how to subvert the kernel if you've got a malicious option ROM. He described it as not necessarily a trivial task. He says no part of the operating system has been loaded when the option ROM initialization is happening. Then during boot, the OS starter brings about dramatic changes in system state. On x86, this happens with a change from real mode to protected mode, then initialization of paging, and further on, you can switch to long mode if your CPU supports 64-bit. In particular, he talked about subverting the NT kernel. What he said was that Windows uses interrupt 10 for accessing the video card option ROM. Interrupt 10 is used for setting the video mode and further outputting pixels. Now, KE386 call BIOS transitions to VM86. And then from VM86, if you've got a malicious ROM, you can locate and modify key kernel structures from the hooked interrupt. However, there's a catch. What happens is that VM86 is actually a monitor. And in the monitor, you can map pages specifically. And for example, if you're transitioning to real mode for the int10 call, then you can skip away and not map the key kernel structures. Or if you're mapping them, you can map them as only readable. So this won't work at all if you've got a safe VM86 monitor. He further goes on to note of likely several other means of obtaining code execution in the operating system. But the paper itself does not talk of the other means and only notes one method using the VM86 monitor, which might fail on any decent operating system. Now he goes on to talk about of course, a rootkit needs to communicate with the remote host. And for this, he talks about you can use a specific network card driver for network ROMs, and then you can transfer anything you want to. He goes on to say that you can abuse PXE. N19 is an interrupt that the BIOS calls to transfer control to the bootloader. It goes through all the enumerated option ROMs, picks one that can actually boot using the PNP expansion header, and then it tries it. If it fails to boot, it goes on to the other one, and so on. So a PXE ROM can hook the N19 interrupt so that as to guarantee control of execution. Then you can use the PXE API, which provides a TFTP connection to download any update to the malicious ROM. Once this is done and you've done what you want to do maliciously, you can carry out the normal boot sequence, restoring control to the N15 interrupt that the BIOS uses. To prevent this, he says we can audit option ROMs, we can retrieve them from system memory, and then we can compare them to known good ROMs from vendor websites. And if the vendor provides hashes, you can compare the hashes. He also says that we can do sanitation checks on ROMs. For example, the ROM data structure provides a class code that should match with the device. You can see which all interrupts the ROM hooks. If it hooks interrupts that it should not, you can avoid that. If the ROM has 32-bit code, you can avoid that. Although, of course, several ROMs do use 32-bit code. So he says that if there's isolated bits of 32-bit code in the ROM, then the ROM could be malicious. If there are specific references to operating systems, it could be malicious. And if there's obfuscated code, it could be a malicious ROM. Then he goes on to talk about the trusted platform module. The trusted platform module provides facilities for generation of cryptographic keys, and you can sign and verify whether a ROM is as provided by the vendor or not. What happens during boot with the TPM is that the TPM stores a core root of trust measurement, or a CRTM, which verifies the integrity of the firmware. Once it guarantees that the firmware is actually what it was meant to be, it transfers control to it. The firmware can then look up option ROMs hashes and compare them against good known values stored in the PCR. The PCR values are as they should be, and if any mismatch is found, then the option ROM can be said to be tampered. Now he says in his paper of 2007 that while many new notebooks and desktop systems contain a TPM, it will take several years before the usage becomes widespread. I've got 3 computers at home and a laptop, and none of them have a TPM. Now, summary of the work was that John Heisman basically described the BIOS boot specification and some bits of the PXE specification and said that these all can be maliciously used. His only good way to subvert the NT kernel might not work if you've got a good VM86 monitor. So we move on to further exploitation techniques. The first question that arises is, what does a rootkit need? You need memory, you need execution cycles on the computer, you need access to peripheral devices, and there are further things that you need, but we'll cover them later. So we come on to RAM. Now, the way to detect RAM on a system, x86 system, is pretty complicated. No sane mechanism existed for a long time. Until then, when code would be written to manually probe for memory, or they would utilize hacks to find out how much memory there is. Soon, some vendors started introducing their own interrupts with the firmware. Eventually, with the introduction of ACPI, a standard came into being, and that was the N15 Interrupt with EX as E820, which gave a system memory map describing each unit of memory. What it returned was a list of entries describing a memory region, its type as to whether it is free or whether it is ACPI reclaimable or whether it is ACPI NVS or unusable, and related attributes. Each call returns base address of the memory region, 64 bits long, the length of the region, again 64 bits, the region type, as I said before, 32 bits, attributes field, which is also 32 bits. Now the termination of this list is specified by a return value of EBX is equal to 0. And since the way firmwares are written nowadays, unordered and overlapping entries in this list is quite common. Thus, it is possible for an option ROM to hook the interrupt and pass on calls to the original handler till it returns EBX is equal to 0. Once it does signify when the termination happens, you can return another entry for rootkit memory with type as bad memory. Now, the way Linux works is that it will sanitize the whole memory map, and once it does that, it will say that this particular memory is bad, and it will clean the memory map, reorder it, and take it to be bad. You can also delete entries entirely, so take away free memory entirely, and no one will notice. Now, execution of the initial rootkit, the part that does this, also requires some memory. Now, the same problem arises with, for example, your network card ROM. It also requires some memory for the initialization of the card and for further provision of the TFTP server, TFTP client. So it adopts the following strategy. You've got an interrupt int12, which returns the number of kilobytes of lower memory, one that lies below the EVDA. You can hook it up, and restore the original values on cleanup. So the same strategy can be used by your malicious rootkit. You can hook the interrupt, take away some memory, and once you have done your basic initialization, taken away memory from the N15 interrupt, then you can restore this value. Apart from the bias, the only other way to check for memory is manual probing. And it's very unsafe, not recommended by anyone. There are things like the ISA memory gap. So if you try to do this, most major OSs don't use it. And the only other way is the interrupts that we already covered. The other thing that we need is execution cycles on the main computer. For this, I suggest stealing a logical core entirely. You can siphon a logical core in the system, and then you don't have to go through more changes at all. So how does the OS know where the logical cores are? And these are specified by either multiprocessor specification tables or the ACPI tables. Both have to be probed for in the EBDA. And the EBDA isn't standard at all. Its location is specified by a real mode segment pointer at 40E. And you can easily override this area. And you can change the length and the location of the EBDA. The ACPI table is the root table is called the root system description pointer, or the RSDP. It has a signature of RSD space PTR space, and lying at a 16-byte boundary. The MP table, called the MP floating pointer structure, has a underscore MP underscore signature, again at a 16-byte boundary. Both of these lie in the EBDA. The MP table also can lie in the upper 1 kilobyte of base memory, but that rarely happens. Now, what the malicious rootkit can do is that it can remove entry for either one logical core entirely from both the tables, or it can scramble either of the table. What happens is that the MP specification was introduced long before hyperthreading. So they don't cover hyperthreading at all, while the ACPI tables do list out all logical cores, including those with the hyperthreaded cores. So you can either scramble the ACPI tables, and then on your system, only the OS will use the MP tables, and it won't get to find out about the hyperthreaded cores. Now, removing entry for one logical core has a few difficulties. How the OS starts a AP, application processor, is by a startup IPI, interprocessor interrupt, to all logical cores, even though this is not recommended. Why it's not recommended is for a very silly reason. The firmware might disable all hyperthreaded cores if it doesn't support it, but it might not remove them from the tables. So it is not recommended to do a startup IPI to all broadcast a startup IPI, but all sane OSs target IPIs to specific cores. Any IPI broadcast further by the OS used to transfer any information between two cores will have to be handled safely by the logical core you have taken. Furthermore, ACPI power events will still describe the core and will go through the OS. We'll look at this later in detail. Scrambling tables has a singular difficulty. The end user will probably notice if their multi-core machine goes to a unicore. The advantages are many. You can use the local APCI timer even on the bootstrap processor. You can set it to periodic and wake up after OS initialization. So the problem described by John Heisman on having significant changes in system state to handle by the malicious rootkit can be avoided by this if your malicious code wakes up significantly after OS initialization. Now, on the PCI bus, you can steal devices. For this, the most popular method I know of is by NetWatch. It's a SMM rootkit, and it requires a network card as well. So what it does is it bothers the PCI peripheral it wants to steal to prevent the OS from configuring the card. For example, they wanted the network card. So every 64 milliseconds, they wrote garbage values over the top of the card's base address registers. And they tried it out with Linux, and Linux timed out waiting for the card. You can do this with any other device, and thus you can at least prevent the OS from using it. Now, rootkit is also required to keep watch on the OS. You can do this with three possible ways. You'd either want to trap interrupts on the system, you'd want to trap memory accesses, or you'd want to trap device interrupts. Trapping device interrupts is significantly different from trapping interrupts due to the way the device state is there. Now, trapping on memory accesses is easy. The virtual memory mappings are described by a structure, and the root address of the structure goes in the CR3 register. The CR3 register is easily readable. You can read the address and find out the virtual memory mappings. Thus, a rootkit that took access of the local APCI timer on the bootstrap processor can wake up after considerable time, after initialization has happened, paging has been initialized, and then you can use the address in CR3 to get the mappings. You can then significantly change the mappings, and furthermore, if you don't want the OS to notice, you can have them in the TLB, change them back, and no one will notice. Or you can hook the page fault handler. You can selectively unmap pages and then get the location the OS trapped on from CR2. When the OS does trap on unmapped pages, CR2 contains the address it mapped on, faulted on. Or you can use segmentation. 32-bit systems still use segmentation, 64-bit don't. They still have a segment pointer, but it doesn't really affect how the limit is there. Now, the global description table is used to describe all the memory segments to the CPU. The GDT is pointed to by a GDT description structure. It has the size of the GDT and the address of the GDT after paging. And the SGDT instruction can be used to get the contents of the GDT description structure. So once you do that, you get the structure in the bottom, the size of the GDT, and the location of the GDT. And with that, you can effectively modify the limit of the above is a entry of the GDT. You can modify the limit of the GDT and of any particular segment entry in the GDT. And then when you would try to access the memory described by it, it would issue a global protection fault, which can be again trapped by the rootkit. If you want to trap on interrupts, similar to segmentation, all interrupt gates are described by the interrupt descriptor table. The IDT is again pointed to by a IDT descriptor, which is loaded into the CPU's IDTR. It has a similar format to the GDTR. It has a size of the IDT and the address of the IDT. And the IDTR can again be saved using the SIDT instruction. Hooking on interrupts is then as easy as saving the IDTR and modifying respective entries of the IDT. We talked about ACPI power events before. ACPI does a system control interrupt, SCI, to handle hardware power management events. This can happen if your CPU is going from a particular state to another, a lower power state, or it is going into sleep. And then you can hook the particular interrupt. And then if you've got only stolen one core, and you don't want the OS to notice any power change, any hardware power events on the core, you can remove trace of the working core by the rootkit. You can also hook onto device interrupts. However, there's a particular problem with device interrupts. Several devices have state destroyed on read. For example, with the 8042 PS2 keyboard controller, if you've got an interrupt from the controller, then you have to read from IO port 60 to get the data from the controller. Once you do that, the data isn't persistent, and you wait for next data from the keyboard controller. So if you hook the interrupt and you read from the IO port, the OS stops noticing any further entry from the keyboard. One particular method I thought of to snoop on the keyboard controller is that you can hook the interrupt and get and process data from the device, anything you want. Then once you're exiting the interrupt and handling control to the interrupt used by the OS, you can enable the TF bit in the flags register. The TF bit specifies that a debug exception is to be generated after each particular interrupt. You can then effectively single step through the actual IRQ handler till the IRQ does IO with the device. And then you can modify register contents and pass back control. So the IRQ handler would do a read from 60 again. You'll pass the read from 60, and then you'll put back in the register the content the controller actually returned. And then you can pass back control to the keyboard handler, to the IRQ handler. As far as UFI goes, the UFI specification states that with the advent of the UFI specification, it represents a chance to escape the limitations implicit in the construction and operation of legacy option ROM images. So yeah, they do that to a limit, in that they introduced a new bytecode format for option ROMs. With this bytecode format, accesses to device is more safe. However, they still retained old x86 option ROM formats. So even though UFI itself switches to 32-bit with paging, or 64-bit, it remains vulnerable to attacks used by 16-bit option ROMs. Now, preventive mechanisms. As the Heisman paper suggested, a DPM is an easy method to prevent such attacks. You would have signed option ROMs, and the BIOS can check if any option ROM is malicious or not, or modified or not. Thus, we should motivate all vendors to have TPMs on systems. Furthermore, UFI presented a real opportunity with bytecode-based option ROMs. We should try to do away with the legacy format. Thus, we can have option ROMs that work cross-arc without duplication in different ISAs. We can secure accesses by drivers and option ROMs. And we can have it so that one driver only accesses their particular device. Any questions? Thank you.